Okay, hello everybody. My name is Nicolai Josuttis and I have to talk about C++17, which is the old version of C++17. The new one is just coming, C++20. Who's using C++17 already? Oh, you want to double check? I got it right? Thank you, I get it. So, let's see. I think if I talk a little bit about C++17, the most important thing is how to combine features of C++17. So, whenever I write my books about the different C++ topics, I try to use all these features together, and interestingly, we find issues or we find benefits we haven't seen before. Sometimes this causes bad surprises. Sometimes this causes good surprises. And my intent here is just that we talk about 4 code snippets and see how they change, how they improve, and how to be aware when you switch to C++17. So you will find them all in the C++17 book. That's sold here to the benefit of include.cpp.org. Feel free to look them also up at the website where you can find them. Before I start, let me just talk 1 minute about initialization. Just in case you haven't seen that slides, I do that with each and every talk now. Because initialization is a bit of a mess in C++. It started all with C introducing the mess already using an equal sign and curly braces. And then we introduced to use parents. And then we introduced and fixed that with using braces, creating even more confusion. I just want to propagate that I recommend by default, not always, but by default, always to use braces, as for example, Howard did this morning in the keynote. The reasons are simple. In most of the cases, they work better than the other ways to initialize. So, for example, they always initialize an object, even with C++20. This will be fixed for atomics. Then we detect narrowing. We detect when values lose part of their value when we initialize them in the wrong area. If you create a vector of int with the elements 8 and 15, it works and does not some strange thing if you use parents. You can only use this way to initialize an object that is a member of a class if you have multiple arguments. It's the only way to initialize enums by numeric values, by integral values, and it also, of course, works for aggregates as it always has done for C++. And by the way, in C++17, aggregates now can have base classes, so this also works there then. Okay, that's not the first example, that's just the prefix. And let me say that we still have no community agreement on how to recommend and what to recommend for initialization. Speaking about initialization, it's not only that initialization is still confusing, we still have some discussions going on. Please let me ask you a short question to all of you. You don't have to understand why I asked this question. It's just that I need this feedback for the standardization of the next standard or the next standards. Well, this is a poll for C++20, not 23. Anyway, so just read this question. Which one of the following functions do you think are safer? Option A, make shared and make unique. Option B, make shared default in it and make unique default in it. So who here in the room thinks option A is safer? Please raise your hand. Oh, thank you. Who thinks option B is safer? Thank you. That will hopefully help us to make C++20 better than I thought. No explanation of this. Let's go to the topic. First example, let's talk about if and traits and guards and locks and yeah, let's see. So assume I have a function that wants to insert an element in a collection. I name it insert as string. You will see in a moment why. So, and it's just a template, and this template takes the argument and pushes it back into the collection. Good. Let's use it in a vector of string, and let's insert this string, or a string literal. That works. Fine. Great. Well, however, if I try to make this even more smarter, and that's why it has its name, and I want to insert an int, how can we do better? And how can we support that? Because this will not compile. And the usual way to support that is to say, well, let's insert into the vector, or let's insert a string, an int into the vector by converting it to string. So you need two different ways to implement this function. One overload for int and one regular implementation if the type fits already. And that's a general pattern here. If I want to add more types, like I want to insert a double here, then surprisingly, the first function is a better match than the second function. That has to do with the rules of overload resolution, which are in general pretty good. They can't be perfect because we have too many ways that are sometimes useful and too contradictory ways that are useful. So by rule, the first function will be chosen and the second will not be used, which means we might add a third overload and say, okay, here's the implementation to insert a double, and so on and so on. So how do we solve this problem in general in C++? That has nothing to do with C++11. Well, in C++11, before C++11, we could partially specialize templates, etc., and use enable if. But what we really would like to have is something like, if my argument is an integer, or it's an arithmetic type in general, let's use toString to insert the element. Otherwise, let's use it as it is, or try to use it as it is. Unfortunately, this does not work, although we have functions to check whether something is arithmetic. This does not work with an ordinary if. This is a compile time error. The compile time error, by the way, applies to all versions now, because in each and every version, some of the code that is instantiated, some of the template code has a bug or has a problem. So, for example, when we try the first version, you get a self-explanatory error message. And in this error message, you see that, yes, we have no toString support here. And by the way, the error message is just one message. It's that long because the compiler tells us nicely what it tried out to have some implicit conversions that might then use toString, etc. So how can we solve that? First feature of C++17, use the compile time if. The compile time if is supported since there, and with that, this is possible. This is okay since C++17. And by the way, if you worry and say, well, if arithmetic t value is a little bit much to type, yes, we have a shortcut also introduced for that with C++17, and it looks like that. Please beware that there are some subtle rules there. And now, as I am on stage, I forgot that I wanted to prepare that slide here. So if for whenever you have other cases and you want to rule some of them out with an assertion, that won't work. Because in template instantiations, and if you have a compile time if, that does not mean that the part that does not apply is ignored. Still, there are rules, things to be checked if this if construct expression is false. For example, in the true part, even in the else statement has to be valid C++, and any assertion or any expression that does not depend on a template argument has to be valid. So if you just have an else part here, or second else part, with just assert false, this will not compile. Still not compile. You need something like assert size of t is not equal 0 or so. So something that depends on type t. So there are still some traps here. Okay, now let me check this out a little bit more. Let's assume we have this in concurrent code. So in concurrent code, we use mutexes. So around this whole call, I try to lock a vector of strings, a vector, and for that I have a mutex to lock it. So let's do it in the head. Fine, looks like that. Code before C++ 17 looks like that. And then we have some change here, something we can do better or more easy, because the problem is, or the issue is, that in classes, in class templates, you always have to specify the type how this template is instantiated with. So here for the lockguard, you have to write again that this is a lockguard for an std mutex. That has gone. With C++ 17, we have class template argument deduction. So even when we instantiate a class template, we can deduce the type by the corresponding constructors, which works pretty fine in this area, which does not always work fine, as we will see in a moment. So, on the other hand, it might be that we say, wait a minute, it might be that insert as string is a little bit more complicated than just this. So it does not only insert the string or whatever we pass and want to convert to a string into a vector, so it might also be that there's more to do. So then it's a better practice not to lock the vector at all the whole time. Let's lock it inside the function. So that might look like this. So you say, inside the function, we create the lock with the lock guard, and then we do the insertion. And for that, we might pass the mutex that belongs to the vector. Okay. Can we do something better here with C++ 17? Yes, we can. Look at these these braces around that. They are necessary to make sure that the guard unlocks and when it gets distracted, so that the other stuff at the end is not done while we are still having the vector or the vector mutex locked. So what can we use here? Here we have another feature we introduced in C++ 17. It's a compile time. It's an if with an initialization. And you can combine these two things. We have now a compile time if, and we can combine it with the feature of an if with an initialization. And that means we initialize an object here before we do or check the condition. So the first part, it's like in a for loop, is the initialization before we do the check. And this initialization creates a lock. And as within a for loop, the lifetime of the thing we initialize there ends at the end of the if, which means at the end of the else, if the else part is used. So, there again is a trap already. Well, first of all, we can extend this to multiple mutexes. So we have a new type called scope lock. This means that we can apply, or that we can, in the constructor of this lock guard, lock multiple mutexes. And as you see, we could now pass a variadic template, so a multiple mutexes as last argument of this function. So the caller can now say, let's pass one mutex, or let's pass two mutexes. Note that the mutexes might have different types. Or pass no mutex at all. If you pass multiple mutexes, this initialization will then use a deadlock avoidance mechanism that was introduced in the global functions std lock with C++ 11. And if you pass no mutex, that's also supported, that's defined behavior. With this behavior, you just don't lock any mutex at all, and the code still works. So this is a way you can say, whatever I have as code, I can make it more variadic, more generic. Somebody can pass me as many as mutexes they want to be logged while this code runs, or while internally some part of the code runs. What else? Yeah, I should say, some people might ask, why did we introduce a new type for that? So why did we call this scope block and not lock guard? And the answer is binary compatibility. We could not extend the lock guard to become a template without breaking binary compatibility. So we had to introduce a new type here. So we have now 3 different lock guard types beside the 7 different mutex types we have. It's getting worse. It's getting like in Java, where you have 10 solutions for everything. Yeah, but I'm sorry. That was a late design or change, and we found that out later. And although formally we are not required to be ABI compatible, in practice we are, because otherwise compiler vendors will stop to support the new features. And please don't make one mistake, which we already have seen here about this cool feature. Because you might say, oh, wait a minute, I don't need a name for the scope block, for the lock guard. So let's remove it. And just let it be declared that way. That's as in the for loop, you create a temporary object, but the lifetime of this temporary object ends with a semicolon in the if clause. So you lock all your mutexes, but you unlock them before you check them whether this is arithmetic, and push things back into the vector. So yeah, there are some issues, but this was already the case with the for loop, but this might be more used than in a for loop. And yes, just if you wonder, the condition is checked at compile time. The initialization is performed at runtime. That's possible. So, I said that already. So let me summarize what we have seen so far. You have seen 5 new features here in this small little line. Compile time if with initialization, scope block, class template argument deduction, and a type trait with the _v suffix, and 1 trap. Well, maybe 2 traps are involved here with the assertion and with the effect of code partially instantiated or conditionally instantiated. And that's something we see in C++ 17. It's a whole bunch of new features. All the features are very tiny, very small. But using them together is sometimes surprising and sometimes very powerful. And the rest of this talk will be 3 other examples. Besides, I have to say something about class template argument deduction. And I think I had at least part of these slides in the keynote last year here. So you should all remember and know that already. Haha, let's see. Here are the vector constructors. And we have class template argument deduction now. So that means if you declare a vector, you don't have to specify the type of the elements if you can derive that from the arguments in the constructor. So that means if you declare a vector taking 2 ints, yeah, the way this works is find the best matching constructor, see whether you can derive the template argument types, and if that works, then try to compile that and see if that compiles. So here, the best matching constructor, which one is it? The initializer list, because if multiple constructors are possible, the constructor, if you use brace initialization, then the constructor with an initializer list has highest preference unless you pass no argument. It's a very simple rule. And so this will instantiate vector for int, and this is also a valid code to compile, so this will work. So with 1 argument, which one is chosen? Still, One argument. Yes, the same. If we don't use braces, which one is chosen? Size and value, somebody shouts here. Somebody else has a different opinion. Well, it can't be initializer lists. They need braces. So yes, that's right. So this creates a vector with 8 elements of value 15. I don't think this is self-explanatory code. Maybe it's better in these 3 cases to specify the type of the elements. But it gets worse. One argument in parents. Which one is chosen? It's the third one here. So it can't be initializer list. We have to have one argument that can be integral. That one is chosen. Here in this declaration, we don't see any t at all. So this will not compile because we can't deduce t from that. So we can't deduce the template type. So that will not compile. Easy? Okay. What's this? Eight of const char star. Yes, C++ has some tricky rules. So it's correct. The one with the arrow, the constructor with the arrow is chosen, but please be careful. We take the argument by reference. So we don't decay the argument, which means we deduce here that the vector should be initialized by an array of 1 character. Yeah? Not const character, because the const is outside the t. Obvious, huh? And unfortunately, that's an error. So that will not compile. If we would have declared this vector to take the t by value here, it would work and compile. Okay, 2 more. Let's create a set of string and initialize the vector with the begin and end of this set using curly braces. What is it? Curly braces and non-empty, always initializer list. Almost always. Okay. That's deduces a vector of set iterators. Yeah, we pass these 2 elements. Obvious. And if we use parents here, well, the one chosen is V7, but again, from this, we can't deduce element type T. So this will not compile. Well, this would not compile if we wouldn't have a nice workaround on that. We have a so-called deduction guide that tells if you get 2 arguments of the same type, please deduce the value type of the corresponding iter types for these types as the element type of the vector. And because of that, here we deduce a vector of string. Good. This is, by the way, the full deduction guide with the last argument being the allocator. So last question, what is this? Well, initializer list takes the arguments by value, so these decays to const character star. So both elements have the same type. So this is a vector of const character star. And what is this? This is a nightmare. So it's again the one here be chosen. So this deduction guide applies. So this is instantiating. Yeah, it takes both types as an iterator. These iterators refer to const characters. So we have the begin and an end of, okay, so we say the position of the high is the begin of our range. After the D, we have the end of our range. Well, caught up at best. Okay, don't use class template argument deduction unless it's obvious what it means. Okay? Good. Second example. Fold expression, evaluation, auto and string literals. And string, that's it. Good. So just as a recap, C++11, we introduced variadic templates. So we could we could implement something like this. We have here a print function taking an arbitrary number of arguments, and we want to print them all out. So we always separately take the first argument and print it out, and for all the other remaining arguments, we recursively instantiate this template again. So that means if we pass 3 arguments, we first print out the hello, call print again for the remaining arguments, print out the second argument, and the last argument is still passed to print. Print takes only 1 argument, which is printed out, and then we call, in the third instantiation, we call print with only 1 argument. The remaining arguments, the list of remaining arguments is empty. So the overload there of a print taking no arguments is chosen, and which is more or less a no-op. So effectively, we compile code like this. That's C++11. With C++17, we can do 2 fixes. One you have seen already. We might use an if here. We can't use the ordinary if because that's a runtime if. We have to use the compile time if, but that works here to end the recursion. Good, but we can do something else. We have now fold expressions. And fold expressions are more or less exactly introduced for a problem you have seen with this code here. This is many instantiations, and instantiations cost time. So if you recursively instantiate, a compiler needs a lot of time to do that. And if we want to apply just the same operations to each and every argument, let's introduce something better, and we did. We introduced fold expressions. They have a very weird syntax. So inside parents, you have at one location on the left or on the right 3 dots, then an operator, and then a parameter pack. So a list of arbitrary number of parameters. And this expands, for example, here that we add all parameters to each other. So you can say, let's fold up 17 plus 4. Let's fold up I plus 1000 plus I. Let's fold up the string high with a string high with a string high, which does not work if it's empty. But for that, we can even have an initial value like here, saying, well, if we pass no argument, let's use a 0 because we add all the values of all the arguments to the 0 here. Okay, I've skipped that. So why do I say that with the variadic template example? Well, we can use it here instead of a recursive application of print. So instead of this code instantiating a couple of times, we can simply write this. We can say print all the arguments. As an initializer, we take std cout, so we send all the arguments to cout. That works. Well, we have one problem. We have no space between the arguments. So how can we get around that? Well, you can take the whole expression, the whole fold expression, as part of a bigger expression. So we could afterwards print something else and send it to cout. But we can't do that inside the expression because the notation of this expression is fixed. This is a version with initialization, so 2 parents, twice the same operator, in the middle the ellipsis, and then on one side an initialization, on the other side the pack. That's the syntax. But what we can do, we can use expressions, as we always could do in variadic templates and also in fold expressions. So what you can do is something like here, saying, well, let's print out all the arguments with a space before. Well, not the first argument. So let's take the first argument separately, and then for all the remaining arguments, let's print them out with space before. Space before is just a helper function printing out, as the name says, a space before the argument, and that's it. Good. Works in C++17. But you should be surprised. Don't take the picture now. It will get worse. Or better. There is a subtle problem in this piece of code. So if you see the effectively compiled code here, in the yellow box, this code would create problems before C++17. Why? Because we have no defined evaluation order of when space before is called. So if you have an expression like this before C++17, the possible output might one of these two. Because we only know that space before is called before its return value is used. But it might happen that twice we call space before, and then we use the two return values and print them out. So we have two spaces, and then the other parameters without the space inside. And that's a rule we always had derived from C. We fixed that. And that's, you might have heard of that we fixed something in with the evaluation order in C++, and that's one example where this applies suddenly, very indirectly. And the motivating examples why we introduced that were similar indirect code. So our operators changed in C++17 so that we have, for some operators now, a guaranteed evaluation order. In the past, we only had it for AND or in the comma operator. And now we have them for some others. That was, by the way, an interesting discussion, because especially the people implementing an embedded system and have to prove the correctness of code would have wanted that we have a guaranteed evaluation order now in each and every operand. On the other hand, those who implement the compiler said, then we get worse performance. So this is the trade-off we made. We made it, in these cases, for C++17. Okay, but there's more. The fold expression has an interesting way to deal with it. You have seen we can use expressions when using variadic templates. But there's one problem. You can say here, let's pass all the arguments to foo. You can say, let's pass all the arguments as a comma-separated list with plus to foo. But you can't do that. You can't say, let's for each argument call foo. That's not supported in C++11, but that's a very, very common case we need in generic code. Let's do something with each and every argument. There was an interesting workaround, by the way, you will see in a moment. But here's a way you can do that now, using fold expressions. The fold expression here says, well, let's apply that we call foo args for each and every argument, and we separate these calls with a comma operator here. So that's the way you can do it now, and the void is only because we have this nightmare of overloading comma operator, which I really would like to have removed in C++. Okay, by the way, the workaround before was this. You could use an initializer list, and in this initializer list, use a comma operator to indirectly do the call, because the initializer list initializations have a guaranteed evaluation order from left to right. You find these things in the internet, of course. Good. Having said that, that means we can rewrite the code a little bit different. We can say, let's take all the remaining arguments, so all but the first one, and let's apply lambda so that we can apply the function, formulate the function within the function we have, and so print out all the arguments with a space in front. So, using the comma operator here. Well, we can do even better. you might say, wait a minute, why do we separate all these arguments with a space? That should be more flexible, more generic. So yeah, let's introduce a template argument here. That's nothing new in C++ 17. But what is new, well, now you can say, or we can call print for these arguments. It will print a space. And if we say there should be a dash between these arguments, that works. Also fine. But what we also have now in C++ 17 is auto as a non-type template parameter. So you can say I can pass anything I like, well, anything templates like, to put it between these arguments. And so auto we have introduced here. And that means, for example, you can place a 42 between each argument. There might be more useful examples. But the interesting other feature we also have, it's now a little bit easier to pass even strings to templates. So you can do it that way. You still need 2 lines, but you can say, let's declare a static object. We need still linkage here. So a static array with comma space, and now we can pass this array of characters to the print template, and that way we can pass a string as an argument to this generic function. Okay, and for those who like everything in one function, they can, inside the fold expression, define the lambda they call for each argument. Why are people nodding their head? Nodding? No, shaking their head. I don't understand. This is cool, huh? Okay, I skipped that. Good. Second example. Let's see. Oh, we have a little bit of time. That's good. Third example. Let's talk about strings, views, and parallel computing. Here's my example. Let's initialize a vector of strings. And the strings are just ID with a number. It's not a very useful example, but you get the idea why I do that. So you get something like that on the right. You have ID0, ID0, ID1, ID1. And as you see, always an element with a lowercase ID is followed by an element with an uppercase ID. OK? So now let's sort it. Good. And as an output, we will sort them according to the ASCII code of this. That means all the uppercase IDs will be in front of the lowercase. And yes, it does not sort them numerically. So 1 will be in front of 10, will be in front of 100, and then comes 2. But that's not the point of this example. The point of this example is that I want to sometimes say, well, let's ignore the prefix here. Let's sort them, but ignore the first 2 characters. So the, let's say, naive way to do it would be to say, let's call sort and pass a sorting criterion. And this criterion, we say, what we care for in sorting is a substring, ignoring the first 2 characters of this string. So we create a substring and compare it with another substring. And now, and that's my point, let's measure how long this takes. And you see that on some machinery, there's something getting slower. As usual, if you have measurements and performance, there's not a proof that it's always the case. But this was on my laptop here with the Intel i7 2 cores with hyper-threading. So these were some numbers. So more or less we doubled the amount of time it takes to create the substrings, or to use the substrings. And the reason is clear, because creating a substring creates a new temporary string. So each time we compare them, we create 2 temporary strings, and then we compare them. And even these strings fall under the short string optimization, so they are not that long. It still takes significant time to sort them that way. Can we do better? Yes, we have a new type called string view. That's a view to a string or to a character sequence. And with this view, we can say, well, let's not create something new. Let's just restrict the view. We see a sequence of characters and use it kind of a string without creating a full string. And then for the string view, all the read operations of strings are supported, so it's simply create a string view of A and then create a substring from there. And let's compare the numbers. Surprisingly, it's becoming even faster on my laptop. That's not a significant proof here, but at least we are in that same area of this sort. So the overhead becomes better. And yeah, that's a thing. We introduce a string view as some kind of cheaper string, but with some problems. As usual, you don't get free lunch in C++. Also, you don't get free lunch. So we have some problems with that, and you have to be careful if you do that, because a string view is essentially something like a pointer, and lifetime issues occur. So the reason we introduce that is if you have some value like this, you can create a string out of that, or initialize a string of that, or you can create a string view out of that. If you create a string out of that, the string copies the value into its own data. If it's a short string, then usually just directly in the string. If you have a long string, then it might even allocate memory, which makes it even worse. If you create a string view from that, you just create a combination of what is the length and where's the location of these characters, and that is significantly faster. You can at all time create a string view from a string, as we have done in our example, creating a string view to an existing string. But you have to beware with lifetime issues. So creating a string view from a string constant is safe, because the string view is there all the time, the whole program. With a string view from a string, you have to beware that the lifetime of the string is long enough when you use a string view. And please note that creating a string view from a string is an implicit type conversion, so you might implicitly create lifetime issues. Well, we all know how dangerous pointers are. There are ways to avoid them. This danger comes now back with string views. So whenever you read view in C++ code, you have to get as frightened and smelly as with pointers. It's very important that you understand that. There's nothing wrong to use a string view, but beware of using it and don't creating problems. I give you one example what can happen. Because even if every programmer in your team does everything right, things can turn out to be very surprising. Look at this example. Let's create a string here for you for high, initialized with a string literal high. Now, some cool guys have written a helper function, and this helper function concatenates two string views, which in itself creates a new object. That's okay. We return a string here, not a string view. So that's okay. We create something new that has a different type of the two things we passed here. Good. Another guy in the project created a cool helper function as a template. It says, I have a helper function that builds the sum of two t's. So it adds the first t to the second t and returns the sum, as a t, of course. These two things in combination are a problem. Because now, if you call sum for the two string views, well, inside the sum function, you create a temporary string, you see it here, and then you return it as a string view, which is okay, it's an implicit type conversion. And this is a string view to a local object, temporary object, that is destroyed then when we leave the sum function. So the moment then we use x, y, you have a runtime error, cordump at best again. Okay, be careful. By the way, who made the mistake here? That's a question I love. Who made the mistake here? I don't think it's the first one. We can arguably discuss whether we, with the standardization, made a mistake by supporting this implicit conversion. But I think the real guy who made something wrong is the one who wrote the template in the middle. Because they made a fatal wrong assumption. They said, whenever we add two t's, the result is a t. And that's not true. When you write templates, auto is your friend. And I've seen style guides already that says don't use auto as a return type in functions. That's wrong. Use auto and return type as functions if you have template code, because the compiler knows better than you what the return type is. Okay, and even if you're inside, build the temporary sum, use auto there. But then you wouldn't not, at least in this case, not run in that problem. We are aware, we are introducing a lot of types now that run into this problem. So on one hand, we got more safer. We introduce value types like optional, variant, any, which are making your programming safer. On the other hand, we have the exact opposite path in standardization where we say we want to get the best performance we can, and that means we create more and more dangerous types in C++. Views, and in C++20 we will get the span types. So whenever you reach view and span, this is a smell for your code to double check the lifetime issues of your code. Please beware. And just let me announce something you might not know, because not everybody knows that. We have tools now in beta to check which find these problems at compile time, not at runtime using Valgrind or something like that. So who knows the lifetime profile tool by Herb Sutter? Almost nobody. Please look at it and make it part of your quality gate when you deliver code. Because they have implemented an idea that was proposed by different people. The approach was always the same. We need a way to express lifetime dependencies for functions, so that the implementer of a function can express, for example, if I create a string view from a string, that this string view lifetime depends on the string. And with this knowledge, the caller of the code, and in this time the compiler, can double check whether we have a problem with the lifetime issues here. And this is not the only place where we have it. We fix with that a lot of other problems in the code. So you see here, the Godbolt link with the lifetime profile extension, which is available for Visual C++ inbuilt. And here you see it as an extension for GCC, and I think for Clang, and they also have it for GCC. You get a clear error message telling me that I have a lifetime problem created in this code. Compile time, not runtime. So I strongly recommend to use a tool like that. Okay. We are not done with this example. Can we do it even faster? Yes, we can, because so far we have not used the new feature that we can run code in parallel. So we would run this code sequentially, but there's this new way that we have support for parallel computing. So if we switch to parallel computing and you compare the numbers, you see we are getting even better. Even for something like 100,000 elements, which is not a lot, we are getting better as the even initial version of sorting. So yeah, we have something in common. And again, you see, should you use parallel computing alone? No. Should you use string view alone? No. Combine these both, and then the performance gets even better. And just as a side note for those who think, yeah, but parallel computing has its restrictions, it does not always apply, let me tell you what I learned when I documented all these algorithms. Because we have this function partial sum, which always computes a partial sum, so 3, then 3 plus 1, then c plus 1 plus 7, when we have a range of values and convert it to another range of values. So I thought, why the hell do we have a parallel version of this? I have no idea how we can parallelize that, because we always have to compute all the values, first the first one, then the first and the second, etc. So this can only be evaluated from left to right. No. We have knowledge in our community how to make things better, even for algorithms that are not intuitively able to run in parallel. And here's a way you do that, just a rough idea. The algorithm uses the following technique. It always combines 2 elements, then 4 elements, then 8 elements, and computes the sum. And then it implies this intermediary sum down, propagates it down to all the existing other values, and suddenly you have the result you want to get here. And this is, here you can use parallel computing at a lot of times. The Intel guys who proposed that said if you have a 32-core application, suddenly computing the partial sum becomes 10 times faster. And 10 times is an issue in our community. So yeah, we can benefit from things like that, also using C++17. Last example, unions, polymorphism, and overloading lambdas. This is a way we learn polymorphism, or we usually learn polymorphism when we learn C++. Create an hierarchy, an inheritance hierarchy. So with a base class, maybe an abstract base class like here for geometric objects, and then the concrete classes like here, circle and line. So the problem with that is you run into a lot of things we really would like to avoid. We run into the problems of that we need pointers, we need new, because we run into lifetime issues, because we can't locally create a line and a circle and put it in a vector to create an inhomogeneous collection of different geometric objects. So we need new, delete, pointers, etc. Yes, we can use smart pointers, but they also have some interesting problems, each and one of them. And yeah, so we need downcasts, but that's the way we use that usually. And please don't forget, before we remove all the elements in the vector, to call delete for all the arguments. And if you want to be safe, and when you call delete, after you call delete, assign a null pointer to the element, you come to this strange situation where you have a pointer, a reference to a pointer in a range-based for loop. Try to explain that to beginners in the first or second week. That's really an interesting experience. So, how do I say that? Well, we have a new thing in C++17, and as a side effect of these new things, of this new thing, we have a new way to implement polymorphism. It's variant. Variant here you see has here is kind of a union, and it has 3 alternatives. There are differences to the inbuilt union. The most important difference is that a variant always knows what it holds, and you can ask for it. So we can assign different things, like a string, like a int, like a long, even with implicit type conversion. Just like overloading, the best fit will be used. And then we can ask, what are you currently holding? I get the index. I can access this type, and that way I can deal with that. Good. So here's a way we change our 4th example to deal with that. So instead of using pointers as elements of a vector to have an inhomogeneous collection, let's use a variant saying my element type is either circle or line. And the interesting thing is a variant is a value type. That means no reference semantics. You can copy it, you can pass it around safely, you have no lifetime issues at all. So you can create a vector of either circle or line. You can push back a line, you can push back a circle, you can return the whole vector, and it works. How do we do the dynamic, the polymorphism? That's a function called visit. So when we then iterate over all the elements in this vector, we call a function called visit, And this visit is roughly doing what polymorphism is also roughly doing when we create the code, namely at runtime decide what to call. And here, for example, we say for each possible element, whatever the type is, we compile the lambda here in the blue box. That's a polymorphic call. That's compiled. That's generic code because it uses auto. That's compiled for both circle and line. If this will not be supported by one of our types, we get an error message at compile time, not a runtime error. And then we call draw for whatever was compiled, and the visitor is more or less a local vtable that decides which of the instantiation of this lambda will be called. No way, no need, no reason to clean up anything, because we don't need pointers, we don't need new, we don't need delete, we don't need smart pointers whatsoever. And by the way, as an interesting side effect, all the elements are now located together in the vector and not distributed over the code. And that means you don't need the base class, you don't need even virtual functions at all. And you could add a third type here, being std string or int, and that would work. So the only question remains is, how can we do a downcast here? Yes, we can. Assume we have get center in a circle. Well, let's use our compile time if to do a downcast. It's called getIf for variant. So if it's a circle, let's downcast it, and if this is not the null pointer, we have a circle, and then we do something circle specific. It's more or less like a dynamic cast here, just with a different syntax. And the only other alternative, which is a little bit more tricky, is you could have a compile time if in your lambda saying at compile time, when I instantiate this lambda, everything is special. The third option, by the way, is overloading. OVLD, that's a capital O, that's nothing from the standard. What is that? My goodness. Overload 2 lambdas? Well, this is overload. This is a small helper template, and this small helper template says, give me in the construction an arbitrary number of function objects or lambdas, and I create you an object that derives from the types of all these lambdas. So that's a function call operator for each and every lambda is available in my object. Did you get that? Doesn't matter. This is using the feature that aggregates have base classes. We had that at the beginning. This is using deduction guides because you don't want to specify, and you can't easily specify the type of the lambdas. So one side effect of class template argument deduction is that now the type of lambdas can be deduced. And we have here something which I didn't tell you, which is a variadic using ... And last but not least, using parents here with overload would be an error, because this is an aggregate initialization. And I told you it's safer always to use curly braces now. And that's here, otherwise you get an interesting error message. So that's it. 4 examples. You got a lot of features which are listed here. You got a lot of traps when combining these features. Not a lot of, but a few. I learned them. And I've documented them. Let me just say what we announced this morning. This book is available here, my C++ 17 book, covering all the topics I just told you. We sell them here to the benefit, to Donna there in the money, to include cpp.org. I just heard half of the books are sold already, so hurry. And that's it. I hope you learned a little bit about C++ 17, and that even a lot of small features can lead to a big and great benefit. Thank you very much.